Introduce to you this afternoon keynote speaker on the topic freshwater ecology. Okay. I don't need to repeat what I just said, no? It is really a pleasure to introduce the keynote speaker on the freshwater ecology topic, Anemarie van Wezel. I thank you, Anne-Marie, for accepting the invitation of the organizing committee. It's really an honor to have you here with us this afternoon. Anne-Marie is the scientific director of the Institute for Biodiversity and Ecosystem Dynamics at the University of Amsterdam, where she is also a professor on environmental ecology. Anne-Marie is also a member of several councils and boards, including the Dutch Health Council and the Dutch Board on Authorization for Plant Protection Products and Biocides. She also integrates the editorial board of the journal Reviews of Environmental Contamination and Toxicology. Anne-Marie has long experience on chemistry and toxicology, risk assessment, and environmental policy evaluations. She managed various large-scale and interdisciplinary projects, and ongoing projects funded by the Dutch Research Council include shale gas and water, TRAMP, Technologies for Risk Assessment for Microplastics, EMERGE, effect-directed monitoring tools to assess the ecological and human health risks of chemicals of emerging concern in the water cycle, and RUST, reuse of treated effluents for agriculture. Our talk today, oh, you changed your talk, your title, will address anthropogenic effect of and use of chemicals and effects on humans and ecological health. We use a variety of chemical compounds in healthcare, agriculture, and industry. And these compounds, together with their transformation products, end up in the environment. And Marie is going to give some examples on non-target analysis using high-resolution mass spectrometry applied within the water cycle and a variety of chemicals that are then encountered. She will also address the manner in which the chemicals are distributed within the freshwater environment and on the toxicological relevance of these emerging chemicals on the context of drinking water production, as well as the model ecological relevance of the mixture of chemicals. The direct measurement of the sum effects of all these chemicals is a developing technology. And then Marie is going to show us some results on the bioassay type of measurements and discuss the interpretation of these effect-directed measurements. She will then finish with some perspectives on possible future policies and mitigation measures. You have more or less 40 minutes to do your presentation, and then we will follow with about 10 minutes of questions. But we'll try not to go over this time because then we have other sessions. So I now leave you the floor to you, Anne-Marie, and thank you again once more for being here.
Thank you for the kind introduction, and thank you also for the invitation by the EEF organization. I appreciate it very much to be here. The title of my talk is Anthropogenic Use of Chemicals and Effects on Human and Ecological Health, or what is the ecological relevance of all these tiny chemicals that we are using day by day. So we use them all. Think about what you did today. You had your food. This food is produced often with pesticides. You are wearing your clothes. When it's not cotton or wool, it might contain chemicals. Maybe you have to use pharmaceuticals, which are also chemicals. When you're a female, you might have used cosmetics with chemicals. You are in this building. There is anti-flame retardants on the furniture. We have the walls painted by chemicals. There are a lot of food additives. These are all chemicals, so we are really surrounded by this. If I refer to the previous speaker, Dan Sanders, she had this toilet paper with only 2 sheets of humankind. Only a snippet of this toilet paper, we are using these chemicals only basically since the 40s or 50s, but it's really very fastly growing. Here you see a slide which was produced by Bernard, in which he compared all factors of global change. And on the left, you see the factors that we traditionally talk about. So like, for example, CO2 increase, biodiversity loss, world population growth, fertilizers, all scaled on this same time scale and all proportional change since 1970. When you go to the right, you see the chemicals. You see the number of chemicals that we use, for example, which are approved in our legislation. You see the volumes of chemical that we use. And you see that this proportional increase since 1970 really outpace these other factors of global change, except for the nitrogen fertilizers. So these are really steep increase of both the numbers and the volumes that we use as society, also you, also me, day by day. All these chemicals, at least the parent compounds, are authorized, and we do a risk assessment for them. So they are used in several sectors. They are produced in industry. They are used in agriculture, both greenhouses, horticulture, livestock. They're used in our households and in the care sector. And we have all these European legislation. We have the legislation for REACH chemicals. We have legislation for plant protection products. We have legislation for biocides, for pharmaceuticals, and for veterinary pharmaceuticals. And in all these legislations, we look at the hazards of these compounds, and we look at what type of exposure do we expect for these compounds. And we compare the concentration at which these chemicals are hazardous for us as humans, but also for the environment. And we compare that to the concentration that we predict to be exposed to. And that's how we say, why we say, well, these chemicals are acceptable, or those chemicals cannot be authorized onto the market, or we have to take some mitigation measures. All these chemicals find their way to the aquatic environment in the end, sometimes via industrial wastewater treatment plants, sometimes via municipal wastewater treatment plants, sometimes, for example, for the pesticides and also for the veterinary pharmaceuticals directly. And these treatments reduce a little bit the load of these chemicals, but in the end, our aquatic system is is in fact a mirror of what we do day by day, and all these chemicals that we use can be found there. There are in the EU large mandatory routine monitoring programs. For example, under the framework of the Water Framework Directive. And there is a list of old friends, well-known chemicals which are studied for decades, which are mandatory monitored for example, including pesticides, and often still found. And here I will go into detail, a little bit more detail on a study on pesticide occurrence, because pesticides are often pointed at as one of the reasons for biodiversity loss. So we did a study in which we analyzed all data between 2010 and 2014 in the Netherlands in this routine monitoring set made by the drinking water utilities. We looked at, in total, 408 pesticides which are now or were authorized on the Dutch markets. And also we looked at 52 metabolites, because a lot of these pesticides, once used and once in the environment, will be degraded, for example, based on photooxidation or based on metabolism or on biotransformation. So that's why we also included those metabolites. And we could trace back in this monitoring set 63 of the pesticides and 6 of the metabolites. In other words, most of the pesticides were not detected or only in really low concentrations. When you look at the concentrations that we find in surface water, in riverbank filtration or dune filtration, which is often used as a source for drinking water production, in groundwater and in drinking water, you see that in surface water we find the highest number of these pesticides and metabolites. In the other matrices we find lower numbers, But if you look at the concentration, you see that in groundwater, the concentrations that we find are all the same x-axis, are even higher than in surface water, which might be a problem for the production of drinking water, because when we use surface water as a source, we have a vast number of water technologies like membrane filtration, ozonation techniques, active carbon filtration, of which we expect that they will reduce the pesticide concentrations. While when we produce drinking water from groundwater sources, we don't have this high number of technologies applied, so there is a lot less removal of this type of chemicals. When we looked at all the sources that we use for drinking water production in the Netherlands, in about 2/3 of the sources, pesticides and the metabolites were detected. And even in 1/3 of these drinking water sources, the quality standards which are set by the Water Framework Directive, also to produce drinking water from, are exceeded. So we still have a problem with the use of these pesticides. And often people ask, how can this be? Because they are authorized, so why do we find these high concentrations? But the authorization is per pesticides with a certain active substance and crop combination, while these same active substances might be used in other crops and also in other pesticides, which are always mixtures, or even as biocides or pharmaceuticals. So the concentrations that we find in the environment are a sum of all these uses by these active substances. When we look at why are these substances problematic, you see here a plot with the octanol water partition coefficient, which is a measure of the hydrophobicity. So here are the more hydrophobic chemicals, and here are the well-soluble, water-soluble chemicals. And you see on the y-axis the degradation. So these are the persistent chemicals, while these are very fast degraded. And you see in the various colors the green, which are not really forming a problem, towards the purple, which are forming a problem. And here you see the criteria that we used for this prioritization. And what you see is that the more water-soluble the chemicals are, and also the less degradable the chemicals are, then they can form these problems. So the mobile and persistent pesticides and metabolites are more likely to be classified as high priority pesticides. And this was all published recently in Chemosphere. However, we authorize new pesticides day by day, and those routine monitoring programs, they take some time before these newly authorized pesticides are taken up. So we also looked at recently monitored authorized pesticides, which are not yet included in the routine monitoring programs. And we saw that 15 out of the 24 were detected in a monitoring campaign. And here you see the recently authorized pesticide, and here you see the concentrations in which they were detected, both in groundwater and in surface water. And you see that 2 neonicotinoids occur in the highest concentration. And you might have heard about the neonicotinoids. One famous one is imidacloprid, which has been not really banned, but very much restricted in its use because of the problems this neonicotinoid poses to water insects and bees. What we often see is that society continues to ask for the functionalities that this chemical has, so there come replacers on the market. In this case, those 2 neonicotinoids. So we often speak about regrettable replacement. We ban one chemical, society asks for its function, so new ones are coming into the market and can be rather quickly after the authorization be traced back in our environments. What we also see is that these surface water are more easily contaminated, and it takes a while before the groundwaters are contaminated, because there is traveling time from the surface water to the groundwater. That's what is reflected here. So in many of the surface water we find back these recently authorized pesticides, while only in a tiny proportion of the groundwater they can be found back. So this was all based on target screening, where we use targets in our liquid chromatography mass spectrometry to compare the environmental signals with the targets that we are searching for. But we use a vast majority of chemicals. People estimate about 100,000. There are millions in the world authorized. We all use them. They can all find their way to the environment. So we also look for techniques in which we can search for a large variety of these chemicals together. And that's why this high-resolution mass spectrometry, for example, orbitraps or QTOFs, can be used. And what you then do is you have the samples and you analyze them with this high-resolution mass spectrometry, and each feature is characterized by a very specific mass, and the mass is so specific that it can only be related to few chemicals which are on your suspect list. So you have suspect lists, for example, made by the Norman network in Europe, for all the chemicals and metabolites that we use, and you can compare your features with the masses on this list. And that's how you can have an overview on your pollutions. You can find patterns in time or in space, and at the end you can also confirm that the feature that you look at is really that structure that you think it is. And this was applied in a study published in already 2016 to a variety of water samples throughout the Netherlands. So we had over 5,000 suspects, which were all chemicals that are authorized in the European Union, both from industrial chemicals, pharmaceuticals, pesticides, and so on. We looked at, could we trace back these exact masses in these 150 water samples, and then we prioritized these. And the type of results that you then get is, here you have all your suspect chemicals, here you have all your samples varying from effluents, surface waters, groundwaters, and drinking waters, and in gray then you see, so these are all individual samples. When there is a gray line, you see the suspect. When there is a black line, it exceeds threshold that you see. So this is the type of results that you then get. And you can compare these results throughout the water cycle. And if you then sum up all the responses of all these chemicals, you see that in the water cycle, going from effluents to surface waters, groundwaters and drinking waters, concentrations are really decreased. This is a log axis. So of course in the effluents, wastewater effluents, you find the highest concentrations. But also the type of chemicals change, because what you retrieve back in the groundwater and also in the drinking water has better mobility, is better soluble than what is in the original effluents. So this again points to the fact that these mobile and persistent chemicals are given the problem. This is non-quantitative, so this is qualitative. This technology of non-target analysis, but very popular and used more and more. But it's semi-quantitative. Here do you see all types of reference compounds, and you see their responses per nanogram of target, and you see that there is an order of 2 magnitudes for about 80% of the compounds. So there is quite a large uncertainty on the quantification, and this uncertainty can be driven away when you have really target compounds, and then you make a target analysis again to really quantify, but then you know the type of chemicals to search for. Of course, this is only on the presence or the occurrence of the chemical, And then you don't have any information about the hazard. How toxic are these chemicals? For many of those chemicals, we don't have open data on in vivo toxicity. So it's very difficult to say something about the risks of these chemicals. And that's why we use ToxCast information. And ToxCast is an open EPA database, so from the US Environmental Protection Agency, where they have high throughput in vitro toxicity information for over 8,000 environmentally relevant chemicals. And they look at all series of endpoints. Endpoints related to carcinogenicity, neurotoxicity, developmental toxicity, etc., etc. So we used this ToxCast database to couple to the data that I just presented that we got via the high-resolution MS database. And so we had data on occurrence, but also data on hazard, and we could make a prioritization again. And this was published this year in the Journal of Hazardous Materials. And what we found is that integrating this exposure and hazard data really helps to efficiently prioritize which of these features should be confirmed to be identified at first. And here you see the occurrence, so the high internal standard equivalents are the chemicals which have a high occurrence in these various water phases: effluent, surface water, groundwaters, and drinking waters. And here you see the concentration which gives a problem in this in vitro test system. And the lower this is, the more toxic these chemicals are. So we have relatively toxic chemicals here, but with relatively low occurrence. So the chance that they really pose a hazard is not too high. We have not so toxic chemicals with low occurrence. The chance that they pose a hazard is even lower. At the other side of the story, we have here high occurrence and high toxicity chemicals. These might become a problem, and we have also in this orange. So in the end, we could rank 500 suspects of the 1,000 suspects that we find back in this high-resolution mass spectrometry. And so this really helps to prioritize these chemicals for further identification and further risk assessment. And of course, these are only in vitro data, so it still has to be confirmed that this chemical is so toxic in vivo, because you have different absorption, different metabolism, different elimination, but it's a good first start to prioritize. If you look at the status of chemical water quality in EU member states, what we know on this is based on this mandatory monitoring in the Water Framework Directive. And you see here the different member states, and you see in orange when there is a problem, and in blue when there is a high quality. So you see quite some differences. And Malay et al. Did a kind of risk assessment based on these monitoring data in the Water Framework Directive. And they looked both at the acute risks and also at the chronic risks. So the chronic risks are those risks after long time exposure. Acute risks are risks really after short exposure, which really have severe population impacts. And you see that at about 42% of the sites, chronic effects are to be expected based on this monitoring data, and only on 14% of the sites, these lethal effects are expected. This is based on monitor data. There are quite some differences between the countries, between the member states, on how they do the monitoring. So we would and what we see, for example, is that France here is posing some problems, which is also related to the high number of chemicals that they hand in to the European Environmental Agency. So we would also like to know what if we model this water quality, and what type of effects should we then expect. And this was done in the context of a big, large European project called Solutions. And there we modeled the water quality of synthetic chemicals in Europe. And we used, in fact, the well-known DPLCR model. So we had drivers of the chemical occurrence, such as population density, land use, standard of living and management practices, which then led to pressures as in the form of emissions of chemicals into the environment, and also how they are distributed over the whole of Europe, which resulted in a status in terms of a concentration of the chemical and an impact in effects of the ecosystem effects. And this we hope is helpful also to formulate good responses. And we did this for over 1,700 chemicals, and we modeled fully spatio-temporal variability in over 10,000 EU catchment areas for 3 years, 36 days per year. And we did this because we know that this current monitoring practices provide only a very fragmented picture, because it's incomplete. We don't monitor for all these chemicals. We can't monitor at all river basins, so that's why we did this effort. And if we look at the simulated concentrations of all these substances at all these sites, you see here, in terms of a logarithm axis again, in grams per cubic meter, you see the variability in concentrations for pesticides, for pharmaceuticals, and for industrial chemicals, REACH chemicals. And we also compared these concentrations that we predicted with monitoring data. We didn't have, of course, full monitoring data sets for all these nearly 1,800 chemicals, but we did have monitoring data for 226 chemicals. And you see that on average our prediction was good. So here you have the model error. On average the prediction was good. It was 65% of the prediction were within 1 order of magnitude compared to the monitoring data, and 90% were in 2 orders of magnitude. And what are the main reasons for uncertainty is the uncertainty in emissions, so the inaccuracy in use volumes and use type. You also see here all the watersheds that we modeled, and you see here the data that we use for this comparison, which is, for example, the Joint Danube survey, surveys in the Rhine basins, in the Iberian Peninsula, but also little river floods in the Nordic countries, which were all combined in this comparison. And then we used those predicted concentration. We combined this with information that we have on species sensitivity distributions for all these individual chemicals. These are based on lab data, lab in vivo data, which are used to make these species sensitivity distributions, and they are summed up. So we call that multi-substances predicted affected fraction of the species, MSPAF, which expresses the mixture toxicity. What you see here is how this toxicity is distributed over all these river basins, in blue for the relatively clean ones, towards red for the polluted ones. And we see that nearly 80% of the sites, to 85%, are expected to show chronic effects. And 16 to 43%, depending if you look at the P50 or the P99, is expected to show species loss due to acute toxicity. So a P99 represents 4 days per year, a P50 represents half of the days per year where this is exceeded. We could also point to the chemicals that pose the largest problems, and these are these industrial chemicals which are authorized under the REACH legislation. So these REACH chemicals contribute relatively strongly to the predicted effects. And we also could prioritize the different basins which are most vulnerable to all these chemical uses. And these are the relatively small basins but with high anthropogenic pressures, for example, because of the population density, but also because of the agriculture. And examples of such basins are the Scheldt, the Thames, the Oost, the Trent, the Ems, and the Humber. But yeah, you see that the vast majority of these European water bodies is modeled to show chronic effects, and also relatively large portions is modeled to show even acute effects. And in fact, these numbers are higher than the numbers that were predicted on the earlier Malay study, which was only based on the monitoring data. So if you model all these chemicals, you see that you expect these total mixture of chemicals to be really relevant for the ecosystem and ecosystem health. We also looked, can we simplify this? Because these are quite complex modelings. So that's why we developed this human impact and water availability indicator, which characterize the different basins in terms of the population pressure upstream compared to the in-stream dilution. And you see here that again, the mixture toxicity, which is predicted, is explained for a large part by this human impact and water availability indicator, but not totally, because there are still 2 orders of magnitude variability. But the use of this simple factor reduces variability significantly. Then often people pose the question, so what, when you go to human health? So what are the human health risks of all these emerging substances? And this was elaborated in a study published in 2018, in which we looked at all the chemicals which can be retrieved in drinking water or in drinking water sources. Often we don't have a health-based standard. In that case, we derived ourselves a provisional guideline value, or we compared with generic toxicity data. And if you look what we did find, and you can see here the aqueous concentration, the water concentration in average, or the water concentration, the maximum, in different matrices. So in drinking, I can't really see. So it's in drinking water, in the sources for drinking water, and the mixed drinking water sources. You see that in most cases, the concentrations that are available in the sources are orders of magnitude lower than they should be to exert adverse human health effects. We had over 600 chemicals which were present in this drinking water or drinking water sources. We selected 160 out of them based on the chemical properties. And we show that the majority of these evaluated substances does not present appreciable risk to human health, but also for about half of the selected substances, we couldn't do a health risk assessment because of lacking toxicity data. So this still is a problem. We don't know much of all these chemicals that we use day by day. We not only look at this chemical analysis, which I presented, but we also look at bioassays. So we have a choice set of bioassays that we can use to assess effects of mixtures in the chemicals, and we can compare this to effect-based trigger values, and that's what we did in this study. So in fact, what colleagues of mine did, Milo de Baat, in a country-wide sampling, and we looked at 45 locations and 21 different assays, and in the Netherlands, and we saw responses in 9 responses exceeding these trigger values in 9 of these 21 assays. when you look at which type of land use where you do these measurements is most vulnerable, you don't really see relationships between the land use, for example, urban, very heavily influenced by wastewater treatment plants, horticulture, agriculture mix, or a complex system. You don't really see relationships between these ecotoxicological risk and the land use. And here you see a kind of hotspots. You see again the different land uses, and you see the different responses to different type of bioassays that we use. You see especially this Calyx for pHs gives responses always, but there are also types of effects. For example, here this cytotoxicity based on polar chemicals that hardly give responses. So this helps to prioritize those locations where you want to go more in depth and where you want to apply chemical analysis to understand what are the types of chemicals which are responsible for this type of response. I will finish off with some water treatment and policy. So what we see is that the stakeholders in the water sector are more and more aware on the presence of all these chemicals, and this is really a strong drive to do something. And what can they do? They can think about, well, how is this going to change? How will this be in the future? But they can, for example, install drinking water treatment, wastewater treatment, but also think about different type of policies. When you think about the water treatment techniques that are used a lot, these are active carbon, oxidative techniques like ozone or UV, or membrane filtration techniques. They all tackle different parts of the total chemical universe. So active carbon doesn't work for the very polar chemicals. Oxidative techniques might produce disinfection byproducts. Membrane techniques work, but you have this brine as a rest product, which also is problematic, and very small neutral compounds will go through the membranes. So you really have to have a set of water treatment techniques to tackle all of these chemicals. When you look at the type of techniques that are most successful, then these membrane techniques, when you look at the removal efficiency, function quite well. You do see lots of variability, though, between the chemicals, but also between studies for one and the same chemical. And that's because there is still a lack of homogeneous approach to test the water, the removal efficiencies by these different water treatment techniques. So if you compare, for example, to toxicity assays, it's really well standardized, and this is not the case for all these water treatment studies. So we published a few months ago in Water Research this study in which we had a large selection of papers. We developed a set of relevance and reliability criteria, and there was, so we started off with 244 papers, only 48 papers fulfilled the relevance criteria, and no paper fulfilled all the criteria that were developed with a huge set of researchers in the water treatment and removal field. But of course, you can do more than treatment alone. You can think about what can you do during the chemical life stages. For example, you can develop greener chemicals, so chemicals which are better degradable. That can be done by industry, for example. You can think about more stringent policies for registration and authorization. You can also think about mitigation options during professional use, such as, for example, spray-free zones, but also during non-professional zones use. So there are lots of options to reduce the chemical pressure on our aquatic ecosystems and our ecosystems in general. If you look at the policies that we have currently in place with regard to chemicals in Europe, you see that it's still a fragmented situation because we have different frameworks for different sectors, for different chemical groups. We have different endpoints which these policies aim to protect. For example, the policies on pharmaceuticals don't protect for ecological effects. And we also cover different parts of the chemical life stages. And we think that when we could harmonize these chemical policies more, use each other's data more, also combine the monitoring activities, involve more modeling efforts, such as the one that I showed you, but also think better about non-chemical alternatives or safe by design alternatives, we can really make a big step for a better protected environment. If we look at the type of, at the amount of studies which are being done on this topic in the ecological societies, it's still a lack of attention in the mainstream ecological journals. You see here the amount of papers on these synthetic chemicals in time, and compare it to the amount of papers which pay attention, for example, to climate change or to CO2 rise. So it's still a neglected, almost neglected area within ecologists. So I think it's a big chance for you all to dive into this fascinating field. So I'm, again, very happy to be invited here. I will thanks again to the European Ecology Federation for the invitation. Thank you for listening. And of course, thanks all my authors and the funders for making this research possible. Thank you. There is one there.
Thank you for this interesting talk.
Okay, did you consider biopesticides in your... Thank you.
So what we did is we looked at all the active substances with a CAS number. So these are basically synthetic chemicals. You expect these differences, but we didn't look at, for example, the bacteria that produce pheromones or something like that. These were not taken into account in these studies. Sorry for that. Other questions?
Thank you for your talk. I wonder if you, during your monitoring, use ecological indicators or bioindicators, because in some studies of my group, we use normally these kind of indicators that in a way they are very useful because they integrate everything.
So what we did use is this calculated mixture toxicity, so the predicted effective fraction of the species, which is an ecological indicator. And what we did use are these bioassays. There has been a big project, a large project, Mars, in which they combined the type of effects that we found in these solution projects with ecological indicators, in which they have shown this, again, this relationship between ecological quality and chemical pressures. Thank you.
Resultados 29.